So it turns out that the weight norms aren't really important. Maybe if we had multiple layers that have large weight norms, that might end up causing the input sizes to blow up drastically. Like, imagine we have 3 layers with a norm of 1000. Then as the inputs go through those layers, at each layer they get essentially multiplied by 1000, so they be something like a billion when they get to the last layer. In that case, we'd have to concern ourselves a little bit more with weight norms. But right now, what really matters is the performance of the agent itself, and not the scale of its weight parameters. So on that note, yesterday we tried out training the agent by having it play against itself. And my impression was that it plays very aggressively, and that is not good. Like, it did learn to fold jacks occasionally, but most of the time it ends up calling down and raising even with them. And that is not a good play. So we could say that the cell play is not working. I thought about it a little, and the most likely reason why that is the case is because it keeps playing against mutated copies of itself. And that ends up... and those mutated copies of itself do have an element of randomness in their actions. And if they have an element of randomness in their actions, then the right thing to do is to just keep calling and raising relentlessly. So if that's the case, then the winners will in the end have a combination of playing against a good player and playing against a bad player. So they themselves will never be good players, but merely mediocre players. That's how I see things right now. Basically, the call of the training that we have right now when it comes to self-play is not correct. So imagine what happens after a single apply updates. Let's see. Here we calculate a mask. Then over here we mutate all of those agents in the ensemble that aren't the winners. And it would be better if we actually save this mask somewhere, so that when we're actually calculating the rewards, that we discount the losers from the previous iterations, which have an element of randomness to them. What we could do, let's see. What's really important is that we change the path probability calculations. Right now we are doing it like this. For example, we calculate the total probability, then we divide it by the player probability. We divide it by the sum of probabilities for a particular player ID over the ensemble. And then we add back the individual probability for the player that is being evaluated. And we have something like 4 agents in the ensemble. Right now it would end up calculating for example, suppose we are calculating probability for player 1, ensemble 1. Then we'd take that probability, multiply it by this one, by this one, by this one, by this one. And suppose the ensemble 3 and the ensemble 4, those are the losers. Those are the ones which were mutated and have randomness to their actions. Then it would be better if we didn't actually consider their probabilities. And we only evaluated player 1, ensemble 1 against player 2, ensemble 1, and player 2, ensemble 2. If we, for example, evaluated the probabilities for the losers, we'd also only play them against the first two agents in the ensemble, and so on. This is why we'd need a mask. And if we evaluated the probabilities for example, player 2, then it would be also against the one in the player 1 and the ensemble 2 player 1. If we, for example, needed to evaluate this ensemble 4 player 2, it would be against ensemble 1 player 1 and ensemble 2 player 1. So we basically completely drop out the probabilities for ensemble 3 and ensemble 4, except for maybe that specific individual probability. And we didn't need to put in a mask. So, for example, let's do it. Let's add a mask. Tensor ensemble ID. And this is a bool. Now, what needs to change is how we're calculating the total probability. And we have the player probabilities. We need to integrate over them, considering the mask. Yeah, so we also need the mask right here. Wait, where is it? Oh, this is actually the return. And yeah, now we have the mask. Here we have the ensemble ID. So let's do it like this. If tensor, actually no. Let's put that like here. If tensor index mask ensemble ID, then if it's a winner, then we consider it. But if it's a loser, then we just return the probability of 0. So what's the problem now? Oh yeah. Oh, oops. I got the arguments the wrong way around here. Sorry about that. And yeah, now we have the mask in consideration here. And what this is calculating are the player probabilities if we integrate out all the elements in the ensemble. Like this is considering what would happen if we, for example, sum up all the probabilities in this column and in this column, and it will return a tensor of two elements. Now that we are considering the mask, it will automatically mask out the losers. The probabilities of these will all be 0. It will consider them as being 0, that is, when calculating this. So let's see. Yeah, I mean, this is okay. The total probability should be correct here, The player probabilities are also correct, and this is also correct. So yeah, we don't have to do anything here, but we have to modify these other cases. And I think we'll go into a time lapse here and fill all of this in. We'll have to extend the cross-entropy method model, so we are actually keeping track of the masks, but that shouldn't be too hard. And so after all of that is done, we'll try self-play on Leduc again. Let's go back to the time lapse. I'm not sure what I'll be using as music in the video, but I hope you're enjoying it. So my dear viewers and companions, what has happened was a pretty big blow to me. The cross-entropy method, despite all our effort, failed to train successfully against a static calling machine agent on heads-up no-limit Holdem. I honestly didn't think I didn't have too great of expectations for the cross-entropy method, but now that we are actually trying it on no-limit Holdem, it is a surprise to me that how bad it really is. I at least expected it to be able to train successfully against a static agent, but it cannot do even that. We are getting some signs of decent performance with a linear model, but it cannot learn anything useful with just that. Maybe it would work if we gave it some good handcrafted features. I mean, I've read paper where people have used it to train successfully on something like Tetris. But there they very carefully crafted the necessary weights to get good performance. And over here, we basically don't have those, and we are training it on raw inputs, so the system is getting overwhelmed. And the only conclusion from this experiment is that the cross-entropy method cannot be used to train the deep nets, at least on something like no-limit Holdem. Maybe on some other tasks it would have worked, but it doesn't work on the one task that we actually wanted to work, so it's useless. There is no point in building up on it. There is no point in trying to bring in tabular CPR and trying to make it work with the cross-entropy method. It still wouldn't work. That's a pretty safe bet to make. So in usual circumstances, I'd still continue with this. At the very least, we could get rid of our approach and go back to what was in the paper by Jonathan Lin. Well, let me just excuse me. Can I resize this while it's still running? Oh, it did work. So it's this paper here. This is the one that kind of inspired me to try, at least try considering doing my own handcrafted rules with the tabular reinforcement learning. I kind of got lazy and instead did a calling machine player, just that. But I thought at the very least, like I explained, that with the cross-entropy method, we could learn to read the board and then scale up based on that. But it didn't work. So what we could do is maybe start off using this approach, and instead of doing this whole thing right off the bat, what we could do is maybe make an agent that can separate out when a player has a king in his hand, a queen in his hand, or a jack in his hand. And maybe we could train tabular CPR using just these 4 states, and that would work better than what we got in like 30 minutes of training the DeepNet. And then after that, we could build on that approach and try out this whole scheme, adding rule by rule. Even though the neural networks are pretty much useless, and it's very unfortunate, everything else that we did we did a lot of very good programming here, and this is masterful, simply. And I'm proud of what we did here. It simply cannot be helped that the machine learning algorithms are very weak. And we do have a parallel tabular CPR, and we could use it to with a handcrafted function like this to train it. And bit by bit, we could get better performance like that. We could, on top of that, we could even implement subgame solving. And subgame solving is like, instead of having these handcrafted features, we could just draw 100 random hands for each of the players, then draw like 100 random hands for the board, and then draw up 100 random trajectories. And since we aren't really using any abstractions like you see here, no handcrafted rules, instead we are just specializing the algorithm for a subset of the game, the performance could sensibly approach the superhuman limit. But doing all of this and then that subgame solving thing would be very, very hacky, and I'm not really into it. To begin with, the reason why I'm into programming is not just because of the act of programming itself, so I really do like getting better at it. I do like functional programming. But I also am enamored with the promise that machine learning promises. I mean, with the promise that the machine learning offers. And that promise is that it could take all this effort into handcrafting features, and you can tell that these rules cannot possibly be optimal. At most, you can get a good agent, but there is no solution. And what I would really have liked to have happened by this point in time is for the research community to have discovered some better machine learning algorithms like the human brain has. And then we could use that as a memory system to just to train a tabular CFR agent on top of it. I had a vision. It's generally considered that the human brain is a prediction machine. If you look at interviews with famous machine learning researchers, for example, Yanel Khan, he'll tell you that the brain is a prediction machine, and many researchers agree with that. And I think that it's not necessarily true that you need to predict the future in order to actually be good at it. If you have a memory system, you could look into your past memories, into its past memories, and reconstruct the future based on that. Much like you could, take an image, corrupt some parts of it in a generative image model, and then reconstruct something that's plausible based on that. In the same manner, you can hallucinate the future, as long as you know how to reconstruct sequences. And I think if you look at how the human brain works, it's very stable. You can pretty much throw it at anything, and at the very least, it would do a good job of memorizing the possible solutions, even if it cannot understand the whole of reality. The algorithms that we have here, right now in this series, we used the cross-entropy method back in 2021. I was using deep reinforcement learning, and it worked very badly. The cross-entropy method doesn't work at all, so I guess the deep learning methods would be a lot better, but we only have choices between bad algorithms and algorithms that don't work at all at this moment in time. So really, what is even the point of doing this? The only benefit that we are really getting is that we are getting better at programming, and we are developing our own library and language. And at least for me, that is a reason on its own. I've been doing these videos for the past 2 years, and I kind of been fishing for a high-paying job, because I cannot really take these algorithms and make a actual superhuman agent like a poker agent that could convincingly beat the other professional players with real money. I mean, we could with just this approach. We could. If you look at the Pluribus paper, they did something similar to this. They did a bucketing scheme, then they did the subgame solving, and they got a player that worked pretty well, and they beat other professional players. So if I was really, if I said to myself that we absolutely had to beat, to succeed at life in poker, and there is no other path, then right now we could take this approach and be successful. As it happens, though, my efforts didn't go unnoticed, and I got a high-paying job. It is at a company called SETI AI. It rents out GPUs for sale, and I'm going to be joining as a part of its software arm. I'm going to try to monetize all the GPUs that they have, so they get better annual percentage returns, and hopefully in such a way justify the high salary that they're paying me. It's very much a financial thing. They're taking a risk that I can do it, and I'm going to do my best to prove my programming skills to them, and all of us are going to make a lot of money if we are successful. So I'd rather do that kind of job for the time being. Right now, while the algorithms are weak, than struggle with the approach in this paper. I mean, we could also do something like use OpenAI evolutionary strategies. This is kind of a mix between evolutionary algorithms that we use, like the cross-entropy method here, and backpropagation. But it would still work poorly. By this point, I'm convinced that pretty much nothing works on NL Holdem. The reason for that is actually not that complicated to understand. Let me show you. Neural networks with backpropagation in something like a supervised learning domain are very good at learning natural stuff, like to separate out images. But if they have to learn the results of programs, and the particular program that I have in mind is this hand ranker. The hand ranker is probably the most complex part of the whole game. And it's very, very non-linear. It's kind of you cannot really encode. You cannot really say what the rules are for certain, but just from the examples. As you can see here, we're doing a lot of sorting. We're doing a lot of pattern matching, and even with hundreds of millions of examples. Training on learning something just like hand ranking, I couldn't get a neural network to learn it perfectly back in 2021. And that was very, very discouraging to me at that time. I'd honestly do, rather than bashing my head against all of this, I'd rather do something that's useful while I research a better way. Right now, I'm slowly getting older as the years go by, and I want to start saving up for my retirement. But hopefully, my retirement won't take too long. And after it happens, I'm going to get back to doing machine learning and making these YouTube videos. Before long, better machine learning algorithms will get discovered that work much more biologically plausibly, and they'll have the capabilities that the human brains do. I think of the human brain as a combination of it being a memory system that you could use like a data structure, much like a Python dictionary or a .NET dictionary or an array. And all the behaviors that humans have, the social adaptations, a personality of a human, that is something that is encoded into the genome. This is like a static program. So the path towards getting to AGI won't necessarily be just scaling things up, but it will be a combination of using a memory system to solve tasks in an intelligent manner. Living in such an era will be great. Slowly, as the time goes on, the GPUs are becoming the AI hardware that I've hoped would one day exist. But the algorithms still aren't there, and the LLMs are basically a bubble. They cannot be scaled to particularly harder tasks than what they are doing now. In my opinion, the LLMs, the large language models, are basically just puffed up char RNNs. I was very impressed back in 2015 when Andrei Karpathy wrote that recursive neural network which could predict the next token, and it would learn to quote plausible Shakespeare. That was pretty nice. And then later we got transformers, and these language models got trained on much larger data sets, but at their core, they aren't any different from character recurrent neural networks, char RNNs. We still didn't get fundamentally better algorithms that we had like a decade ago. All the most of the advancements are pretty much noise. They're basically discoveries about what we could really push backpropagation based models to do. They aren't necessarily the next step to intelligence. And merely researching backpropagation based models will not necessarily get us to the next model family. I don't know what will get us to the next step. Maybe the neuroscientists will get. I mean, given enough time, they will come to an understanding of the principles that govern biological brains, and at that point, we'll be able to make much better models, assuming the research community doesn't get there before the neuroscientists do. Since I've been in talks with the company CTO, and next week I'm going to talk with the CEO about my compensation, and after that I'll be starting work at the company. So I won't have time to do my own programming and make these videos, not nearly as much. Maybe I'll make some videos about. Maybe we'll make some videos about supervised learning, maybe how to build image generation models and large language models from scratch and train them using backpropagation. Maybe we'll try out the bucketing method from the paper by Jonathan Lin. I don't know. But I don't really have anything I'm particularly interested in with regard to my own programming. I am quite looking forward to the job. Until one day, neural networks can learn functions like these programmatically. I mean, using just examples. I think I'll take a break. Hopefully, this break from YouTubing, and making videos won't take too long. If you like this channel and like the video so far, do like and subscribe. And I'm going to see you eventually. Cheers.